From the flowing strands of our DNA to the encryption algorithms securing our digital lives, our world is built on massive sequences of data. But when you string millions of variables together, the resulting sequence becomes so overwhelmingly large that trying to analyze it as a single continuous unit is computationally impossible. This diagram illustrates how we solve that problem in basic arithmetic. We use integer factorization, breaking a massive number down into its prime number components to understand exactly what it's made of. Mathematicians realized they needed an identical tool for sequences. They needed a reliable way to strip away the noise and isolate the raw, indivisible building blocks of any dataset. Identifying these indivisible blocks provides the structural blueprint we need to dismantle, analyze, and secure the complex datasets used in everything from evolutionary biology to global cryptography. The mathematical answer to this problem is called the simple permutation. A sequence is considered simple only if it contains no hidden consecutive blocks of values. If we extract the middle section here, 6, 4, 7, 5, and sort it numerically, we get 4, 5, 6, 7. This unbroken interval means the entire sequence fails. A true simple permutation perfectly resists forming any neat consecutive patterns. It exists in a state of pure mathematical scattering. This diagram shows all 6 arrangements of 1, 2, and 3. Let's test them. They all fail. In 1, 2, 3, 1 and 2 form a continuous block. In 1, 3, 2, 3 and 2 sort into a block. Every arrangement naturally groups into an unbroken chain. There are exactly 0 simple permutations of length 3. Absolute mathematical scattering simply does not happen at this small of a scale. If we step up the scale to sequences of 4 digits, we have 24 possible combinations. Out of all those options, exactly 2 survive the test. This diagram maps out one of the survivors, 2, 4, 1, 3. The gap between 2 and 4 is too wide. The gap between 4 and 1 is too wide. Even if we check groups of 3, like 2, 4, 1, they sort to 1, 2, 4, missing the 3 entirely. No continuous intervals exist. As the sequences get longer, the math scales aggressively. For a sequence of 9 digits, there are exactly 362,880 possible arrangements. Only 28,146 of them are simple permutations. This visual plots out one of those successful 9-digit sequences. Notice the extreme gaps. The jump from 1 to 7 spans 6 digits. The numbers are scattered so erratically that they never pack tightly enough to form a continuous interval. As we move toward even larger sequences, a surprising pattern emerges. While the individual counts remain complex, the overall probability stabilizes. For massive strings, the chance of a randomly generated arrangement being simple eventually settles at 1 over Euler's number squared, roughly 13.5%. While identifying exact simple permutations requires heavy computation, the universe operates on a hard-coded, predictable probability for pure mathematical chaos. To understand why these simple permutations matter, think of them as the frame of a much larger structure. Every complex sequence can be mathematically broken down by taking a simple permutation and inflating its individual points with other, smaller patterns. This process, called substitution decomposition, reveals that these simple strings are the indivisible building blocks of all mathematical sequences. This concept is heavily utilized in computational biology. When researchers map physical genetic structures, like these metal base plates representing DNA, they are working entirely with massive, complex sequences. Scientists compare different genomes to track how chunks of genes have physically moved together, completely unbroken, over millions of years of evolution. A sequence of genes in a fruit fly might simply be a rearranged version of the exact same genes inside this mosquito. Programmers write algorithms to scan these DNA strands looking specifically for simple permutations. Finding one means they've isolated an extreme evolutionary case, a total structural rearrangement where 0 contiguous blocks of genes were preserved intact. By identifying these irreducible genetic sequences, biologists can draw a structural map that pinpoints the exact moments and locations where evolutionary branches broke apart. The same principles govern computer science. In digital security, engineers rely heavily on a cryptographic requirement known as data diffusion. Diffusion means taking a tiny, localized change in your input data and spreading it completely and unpredictably across the entire output. This diagram shows a single data point entering a simple permutation matrix. Because simple permutations mathematically avoid forming predictable blocks, the output scatters into a completely unclustered, erratic pattern. This exact mathematical framework of unbreakable scattering forms the architecture behind modern encryption standards, including AES. We rarely see these sequences explicitly named in the software we use daily, but these irreducible prime numbers of data act as the silent engine, tracking our biological history, optimizing our algorithms, and keeping the digital world secure.